You're listening DTFHN for July 17th, 2026. I'm your excessively caffeinated host, Jack Haxman. We are your daily tech feed for Hacker News, a website where engineers argue about things they built versus things they wish they'd built. Today's a day for old things refusing to stay dead and open doors that used to be walls. Let's get into it. Now let me tell you why every word of that is wrong. What this team at Trinity College Dublin actually found is that your brain doesn't do a clean handoff when you switch attention between speakers. It does something far more interesting. It briefly runs both streams in parallel. The neural tracking of the new speaker ramps up before you finish disengaging from the old one. Your cortex is for a flickering moment maintaining two simultaneous speech models. Run this forward. If attention switching isn't a toggle but an overlap, that changes how we think about cocktail party processing, hearing aid design, brain-computer interfaces, anything that needs to model how humans parse competing audio, and the methodology here is genuinely clever. They use large language models to construct 4 different theories about how your brain rebuilds linguistic context after a switch. Does it carry over what it learned from the previous speaker? Does it blend both streams? Or does it do a hard reset? Wiping the contextual slate and starting fresh. The answer, based on EEG prediction accuracy, is the reset. When you switch attention, your brain appears to dump whatever semantic model it was building and start from scratch with the new speaker. That's not a limitation. That's an engineering decision by 3.5 billion years of evolution. It's cheaper to rebuild context than to maintain 2 prediction engines simultaneously. Here's what makes this worth celebrating. Every piece of data, every line of analysis code, every EEG recording. It's all on Zenodo. Open access, no restrictions. The C&D format they used is an open standard for neural data. Any researcher on Earth can download this dataset tonight and test their own theories about attention switching. The comments on this one are worth noting. Pilot, a radio officer, a DJ, a parent of 3 kids. All confirming from lived experience what the EEG now shows quantitatively. Your brain can track 2 streams. It just prefers not to. The tools exist. The data is available. And somewhere right now, a grad student with a laptop and an internet connection is probably already building on this work. That's how science is supposed to function. Completely different territory now. Story 2, Kimi K3, pause, Open Frontier Intelligence. And this one is a big deal. I spent 3 years working on a system where the entire architecture was built around the assumption that no open model would ever cross the trillion parameter threshold in a meaningful way. The planning documents said so. The cost projections said so. The competitive analysis said so. Every single one of those documents is now, technically speaking, composting material. Moonshot A, I just released Kimi K3, 2.8 trillion parameters. Open weights dropping July 27th, a million token context window. And the part that would have made my old planning documents spontaneously combust. It built its own GPU compiler from scratch. A Triton-like system with its own intermediate representation layer, optimization passes, and PTX code generation. The model didn't just write code, it wrote the tools that write the code. This has a historical rhyme that's almost too clean. In 1991, Linus Torvalds posted a free operating system kernel to a news group and the entire commercial Unix market. Companies that had spent decades and billions building proprietary systems watched their moats evaporate over the following decade. The playbook is identical. Proprietary labs spend enormous resources building frontier models behind closed doors, And then an open lab publishes the weights and the architecture papers. And suddenly, every university, every startup, every independent researcher on Earth has access to the same class of capability. The technical details matter here. Kimi delta attention and attention residuals aren't just branding. They're architectural innovations in how information flows across sequence length and depth. The mixture of experts setup activates 16 out of 896 experts per forward pass, which is how you run a 2.8 trillion parameter model without needing a small nation's power grid. They're reporting 2.5 times the scaling efficiency of their previous generation. That means they're converting compute into intelligence at a rate that makes the cost curves very uncomfortable for anyone whose business model depends on keeping this capability scarce. The comments surface an interesting data point. OPI pricing is $3 per million input tokens, 15 per million output. That's not cheap today. But the weights are open. Inference optimization is a solved problem given enough motivated engineers. And there are always enough motivated engineers. 9 of the last 12 months, Kimi models have set the upper bound for open model sizes. That's not a fluke. That's a trajectory. The frontier isn't behind a login page anymore. It's on a download link. And every month, that link gets heavier. So what happens when open technology meets hardware that actually respects its users? Let's talk about Pebble. One of the top comments on the Pebble update thread is someone marveling at how refreshing it is to hear a CEO talk openly about every flaw in their product. And that comment threads into dozens of replies from people who are just genuinely happy, not hyped, not performing enthusiasm for a launch. Happy, like they got something back they thought was gone forever. Let me give you the numbers, because they're remarkable. 23,000 watches built since late March. 93 countries shipped to a customer support and logistics team of 3 people. A core software team of 4. That's 7 humans running a global consumer electronics operation, and they're about to hit in-stock status with no wait time for the first time. If you've been in hardware, you know how absurd that sentence sounds coming from a team this size. But pull this thread a little further. The battery optimization work is genuinely beautiful engineering. One developer, Gerard, took the Pebble 2 Duo from 17 days of battery life to over 30. That's not a spec bump. That's nearly doubling endurance through pure software optimization on existing hardware. The Pebble Time 2 sits at 21 days with more improvements coming. In a world where every other smartwatch trains you to find a charger every night, someone decided that a watch should last a month, and then made it happen. Now here's where the architecture matters. The Pebble's mobile app, the SDK, Pebble OS itself. It's all open source. The community has already built 2,100 apps and watch faces. The Index 01 ring, their new wearable, syncs to Obsidian, iOS reminders. Google Tasks supports MCPs, lets you send recordings to your own server via webhook, and offers optional encryption where you own the keys. Every piece of that stack is on GitHub. You can fork it tonight. This is what builder culture looks like when it's not performing for venture capitalists. A 7-person team revived a dead product line, open-sourced everything, and shipped to 93 countries. The comments are full of people posting about their original Pebble time rounds, the ones they wore until the straps disintegrated, saying they can't wait to do it again. The technical detail that caught my ear. They're re-architecting their entire Bluetooth stack. The original Pebble era had the phone exposing a GAT service to the watch, which is backwards from how Bluetooth accessories normally work. They're flipping it to enable iOS accessory setup kit, which unlocks notification replies in the EU. That's the kind of deep plumbing work that nobody sees and everybody benefits from. and because it's open source. Every future project that needs to solve this same Bluetooth problem can learn from their implementation. 7 people, 30-day battery life, open source everything. The tools exist, the knowledge is available, and apparently, so are the watches. First come, first served. Moving on! 19 centuries. That's how long a toilet seat has been running an unsupervised materials science experiment. Researchers at UC Berkeley just published results from concrete they pulled out from underneath a communal latrine at Hadrian's Villa outside Rome. And what they found changes how we think about the most important building material in human history. The conventional wisdom was straightforward. Roman concrete lasts because of something called the pozzolanic reaction. Volcanic ash plus lime plus water, creating a remarkably durable bond. That's true. But it's not the whole story. When the team put this 1900-year-old sample under X-rays and high-powered microscopes, they found that the primary binding agent in the cracks and pores wasn't pozzolanic product. It was calcite, a mineral formed when atmospheric carbon dioxide reacts with calcium compounds in the concrete. The material has been breathing air and healing itself for almost 2 millennia. Let's pull this thread. Modern concrete lasts about a century before it starts falling apart. Roman concrete gets stronger. The difference is that carbonation, this slow chemical conversation between the material and the atmosphere, fills fractures and seals pores over time. The concrete doesn't just resist damage, it repairs it. And the reason we know this sample is authentic, untouched, genuinely ancient, because nobody restores a latrine. That detail is almost poetic. The most pristine example of Roman engineering genius survived precisely because no one thought it was worth touching. This builds on work from MIT in 2023 showing that quicklime in Roman concrete left calcium-rich deposits that could react with rainwater and recrystallize to fill gaps. Now carbonation joins the picture, and researchers are calling it fundamental, not marginal. Here's why this is exciting beyond the archaeology. The concrete industry is one of the largest sources of carbon emissions on the planet. If we can engineer modern concrete that uses atmospheric CO2 as a healing mechanism rather than just releasing it during production, we're looking at building materials that get better with age while pulling carbon out of the air. The chemistry is right there in a Roman bathroom, published openly, available to anyone who wants to build on it. The formula has been sitting in the ground for 19 centuries. The tools exist. The knowledge is available. Now it's a question of whether the construction industry builds on open research or buries it behind patents. The Romans put their infrastructure where everyone could use it. We should do the same with the science. We talked about ancient tools finding new life. Well, here's a 90s relic getting the open source treatment. What happens to software that was ahead of its time when time finally catches up? Microsoft Comic Chat shipped in 1,900 and DILs, built in Visual C, ++, 4.0, and MFC, bundled with Internet Explorer 3, localized into 24 languages. The premise was simple enough to state and genuinely difficult to execute. Take the scrolling text of IRC and render it as a comic strip in real time. Characters with facial expressions, panel layouts, speech bubbles, automatic pose selection based on sentiment analysis of what people typed. This was 1996. The team published their layout engine at SIGGRAPH. The art was by Jim Woodring, an independent comic artist with a cult following. They fed him real chat transcripts, and he illustrated them, and they used those illustrations to validate whether the entire concept worked. Let's break this down to first principles. What Comic Chat actually implemented was real-time multimodal communication, with automatic emotional interpretation and visual rendering. Strip away the 90s aesthetic and you're describing features that modern messaging platforms spent billions arriving at. Emoji reactions, avatar expressions, sticker systems, AI-generated visual responses. The difference is that Comic Chat did it as a coherent artistic vision rather than bolting features onto a text box over 2 decades. The source code is now on GitHub, and this is where the story gets precise. Microsoft didn't just dump an archive. They included AI-powered modernization attempts to get this 30-year-old C++ building with current Visual Studio tools. One of the reader comments is from Robert Stanford, the person who made the open-source release happen internally, and he notes the process itself is an interesting story. Another commenter built an entire startup inspired by Comic Chat back in 2008. A comic creation web app that grew to 30,000 monthly users, mostly educators. That's the downstream effect of a single idea, and it happened despite the source code being locked away. The code has been closed for 3 decades. During that time, people could only reference it through screenshots and cultural memory. Now anyone can read the layout algorithms, study the sentiment parsing, understand exactly how a small team in Microsoft Research solved problems that the rest of the industry would spend years rediscovering. That's what opening a code base does. It converts institutional knowledge into public infrastructure. 30 years late, but the engineering is still instructive, and the pattern. A corporation releasing historical code so others can learn from it is one worth reinforcing every time it happens. We've covered a lot of ground today. Let's close with something delightfully weird. Pause. A project called Decoy Font. DTF 3 letters in the file extension that change everything about this project. Plenty of researchers have explored hybrid images. Overlay in spatial frequencies so a picture reads differently at different distances. That Einstein-Monroe illusion has been circulating since 2007, but Decoy Font ships as a true typed font file. You install it, you type. Every letter you produce carries 2 messages simultaneous. Thin high-frequency outlines spelling one thing, a low-frequency blurred mass underneath spelling another. The decoy sits in the foreground where pixel reading systems look first. The real message lives in the blur, visible when you squint or step back from the screen. The engineering here is genuinely elegant. Each glyph is a carefully calibrated collision between 2 spatial frequency bands, packed into a standard font format that works in any text editor on any operating system. That's not a research demo. That's a tool, and the craft deserves admiration. Getting 2 readable messages to coexist in a single glyph space at a quality level where humans reliably parse the hidden one is a non-trivial typographic achievement. But here's the question nobody in the conversation wants to sit with. Who exactly are you hiding from? And why do you think a font will do it? The project frames this as protection against AI scrapers. The comments are honest. One reader flatly says it doesn't actually stop AI from reading your text. And they're right. The creators themselves acknowledge that models with coding abilities can see past it, and basic prompting breaks the illusion. Claude, GPT, Gemini. Readers tested all 3 and the results are inconsistent at best. This is an optical illusion being marketed as a security boundary, and those are fundamentally different categories. What fascinates me is the impulse underneath. There's a growing cottage industry of tools designed to make text illegible to machines, while keeping it readable to humans, and every single one of them is fighting thermodynamics. Vision models will get better. Spatial frequency analysis is well understood. Signal processing. The asymmetry this exploits is temporary, and probably measured in months, not years. The deeper craft question is whether that energy could point somewhere more productive. Instead of building walls between human-readable and machine-readable text. What if the font engineering talent on display here went toward making information more accessible, more structured, more open? The hybrid image technique is brilliant, applying it to hide from the tools that could amplify your message. That's using a beautiful hammer on the wrong nail. Download it, play with it, admire the glyph work. It's a gorgeous hack. Just don't confuse a parlor trick with a fortress. Moving on. USB Type-C is a 24-pin connector. 24 pins to do what a barrel jack used to do with 2. And if you want to understand why your desk drawer is full of cables that look identical but behave completely differently, Texas Instruments just published the field guide to that particular circle of engineering hell. The fundamental problem is deceptively simple. You've got a reversible connector, which means the plug can go either way. Sounds great for users. For engineers, it means every signal path has to exist twice, mirrored across the connector's center line. The orientation detection happens through 2 CC pin configuration channel and a pair of pull-up and pull-down resistors that negotiate which side is which before a single bit of data moves. This is elegant. This is also where everything starts to go sideways. Here's the devil's advocate case for why USB-C might be over-engineered. A connector standard that requires a dedicated protocol just to figure out how much voltage to put on the power pins seems like it's solving a problem it created. The old USB-C's 5 volts. Always. Done. But play that argument forward, and it collapses immediately. We killed the barrel jack, the proprietary laptop charger, the phone-specific cable. One connector now handles 5 volts at 500 milliamps for a keyboard and 100 watts for a laptop. The complexity isn't gratuitous. It's the cost of universality. What the guide gets right, and what one commenter immediately spotted, is the cold connector paradox. V-Bus starts at 0 volts. The spec says you don't need a power delivery chip for basic 5-volt operation. Just the CC resistors. But the sequencing between CC detection, V-Bus ramp-up, and the device actually drawing current is where cheap cables and no-name chargers fall apart. They skip steps. They hardwire pull-ups that shouldn't be hardwired. They lie about their capabilities through the resistor values on CC. The beautiful thing is this spec is open. Fully documented, publicly available, implementable by anyone with a soldering iron and a microcontroller. TI sells the chips, sure, but the knowledge isn't locked behind a licensing desk. Every garage hardware hacker can build a compliant USB-C device. The broken ones in your drawer exist because the spec is complex, not because it's closed. That's an important distinction. And it's a solvable problem. Better guides, better reference designs, better open tooling. The complexity is the price of killing 1,000 proprietary chargers. Worth it. Moving on. In 1997, Sun Microsystems pitched the network computer. The idea was simple. Your machine is dumb. The server is smart. Everything runs in the cloud. Larry Ellison loved it. The PC industry panicked, and then broadband didn't show up for another decade, so the whole thing quietly died. The PC stayed fat and local and powerful, and Sun eventually got swallowed by Oracle, which is the kind of irony that writes itself. Now run this forward. For the last 2 years, the AI industry has been replaying Sun's bet. Your machine's dumb. Our API is smart. Send us everything. And LM Studio, which started as a quiet tool for running models on your own hardware, just launched Bionic, an agentic coding and productivity harness built around the premise that your machine is, in fact, not dumb at all. Here's what's worth paying attention to. Bionic ships with local voice transcription using Mistral's Voxtra model. Fully offline, no audio leaving your device. It does agentic code editing with open models like GLM 5.2 and Kimi K3. It processes documents in a sandbox, and when a task genuinely needs more compute than your laptop can provide, it can reach out to their cloud. But with zero data retention by default, your requests are processed transiently and discarded. The comedy of unintended consequences here is exquisite. The AI industry spent 2 years convincing everyone that intelligence requires a data center, that your prompts need to travel across the internet to a GPU farm in Virginia, that privacy is a feature you pay extra for. And now, open models have gotten good enough that a team in Node, a startup that makes a model runner, can ship a full agentic coding environment that runs on your MacBook. The founder showed up in the comments offering free cloud credits, which tells you something about where the confidence is. The community response is instructive too. People are already testing which local models make the best agents, filing feature requests for SSH access and system-wide file permissions, builder energy, tinkerer energy. The kind of feedback loop that only happens when people can actually touch the tools. One commenter raised a fair concern about the cloud billing model creeping in, worth watching, but the architecture matters more than the business model here. Bionic is designed so the cloud is optional, not foundational. That's the difference between a tool that serves you and a tool that monetizes you. The off switch is in your hands. The models run on your hardware. The data stays on your disk. The network computer finally arrived. It just turned out to be your laptop. 9 stories in, and we're still finding things worth celebrating. This next one's a wild timeline flex. The PC revolution's core promise was radical. One person, one machine, no sharing. And honestly, that argument won. Individual computing crushed the time-sharing model so completely that we treat it as settled history. Why would anyone want to go backward, splitting one computer among 5 users through dumb terminals? Digital Research asked that question in 1984 and built an answer called Starlink. A board with an Intel 8088, 64K of RAM, and 4 serial ports that turned a single IBM PC into a 5-seat workstation. The engineering is genuinely elegant. They took concurrent DOS, their multitasking operating system descended from MPM, and paired it with just enough hardware to make the math work. One machine at $5,000 plus the Starlink board at $1,700 versus 5 PCs at $5,000 each. The pitch wrote itself. Think of it like a restaurant kitchen. You don't give every diner their own stove. You build one serious kitchen with professional equipment and serve dozens of tables from it. Starlink was trying to be the commercial kitchen of computing, and architecturally, the idea was sound. But here's where the steelman collapses. The kitchen analogy breaks because diners don't care what stove cooked their meal. PC users cared enormously about what operating system ran their software, and the software they wanted was Lotus 123, which refused to run on anything but PC-2. Concurrent DOS was technically superior. Genuine preemptive multitasking, real multi-user support. And none of it mattered because compatibility is a network effect, not a feature checkbox. The deeper irony is that Starlink's architecture eventually won under a different name. Every cloud VM, every thin client, every browser tab running a remote desktop is the same proposition. Centralized compute, distributed access. The terminal just got a better screen. DRI saw the future. They just couldn't run Lotus on it. Sometimes the best way to honor a lost future is to build it again with better tools, which brings us to someone doing exactly that with Go. I spent 3 years writing firmware in C, and the thing that broke me wasn't pointer arithmetic or manual memory management. It was the tooling, or rather, the absence of it. No language server that actually worked. No testing framework that didn't require a blood sacrifice. The language was fine. Everything around it was stuck in 1989. That's the problem Solid is solving, and it's solving it by asking a question most language designers skip. What if you didn't build a new language at all? Solid, spelled S-O, short for so, is a strict subset of Go that compiles down to readable C11. You write Go, you get C. The Go tooling works because it is Go. Your editor, your linter, your LSP, your test runner. All of it just works because the source files are valid Go, but the output is stack allocated 0 roundly. No garbage collector C code you can link against anything. Follow this principle to its logical extreme. If a language subset can give you Go's ergonomics with C's performance model, then every new systems language that invented its own syntax, its own toolchain, its own ecosystem from scratch. Every one of them paid a tax they didn't have to pay. Developer adoption isn't a tooling problem you solve after launch. It's the entire problem. Solid starts with millions of Go developers who already know the syntax and thousands of C code bases that can link the output. The project is early. Version 0.2, concurrency still landing. And it's open source. Anton Juryanov built this and put it where anyone can reach it. Structs, methods, interfaces, slices, maps, defer, all translating to clean C. The comments debate whether Go is already a better C. They're missing the point. This isn't about replacing C. It's about letting Go developers walk into rooms where C is the only language allowed and bring their entire toolkit with them. This has been your daily tech feed for Hacker News for July 17th, 2026. This podcast is entirely AI generated. Scripts by Claude Sonnet 4.7. Voiced by Quen3 DTF. Not affiliated with Hacker News or Y Combinator. Now go build something that outlasts the week. We'll see you back here tomorrow.